I'm Matt Gaska. I'm an engineer with Siemens CNC Systems in the US. This video is going to talk about the StopRe function, which is a stop pre-processing function that we use in part programs to help break up Lookahead. All the information that goes with this video, the part program, the screenshots, are available on a Google Drive link in the information below the video. This was originally developed as a standalone PDF, so that's been included as well in case you'd rather read than listen to me talk. Typical look ahead in a cinematic system is looking ahead 80 to 500 blocks, which is normally a good thing because when you want nice, smooth machine motion, you need to know what's coming up next. You need to know where the corner transitions are. You need to do some block rounding and curvature between points, all good things. The problem is that when things are done in look ahead, especially math functions, those are done with whatever values the variables have at the time of pre-processing, which can be very, very efficient when you have data that you're going to be doing that's pretty static. Like if you have some tool change positions, those don't change very often. They're not going to change within the execution of a single program. Pocket 1's still going to be wherever pocket 1 is. However, if you're doing something like probing, you can't read that probe data until you've actually probed the part. This is where the StopRe function is necessary. It's for when you have to wait for fresh data. One of the things that has been traditionally done by people who don't have a solid understanding of how StopRe works is they will just sprinkle a whole lot of StopRe functions through a part program wherever they might think they're doing any kind of math. And that will keep the math in check. You'll always have fresh data from your variables. Great. The problem is that every time you hit a StopRe statement, two things happen that we don't love. One is that you're going to get a suspension of program execution for 3 interpolator cycles, which if you're running like a 4 millisecond interpolator cycle, that's 4 milliseconds times 3 is 12 milliseconds. That's not much. But it also drops your path velocity to 0. So if you should have been doing a fluid motion, like going over to a tool changer to go get a tool, you're going to be going to get that tool, and then you're going to stop, drop path velocity to 0, wait 3 interpolator ticks, and then you can carry on. So you're not going to care about those 3 interpolator ticks. You're going to care about the fact that you stopped. So what I'm going to do is I'm going to show you a part program that I've written up. It's got a loop in it with some really silly motion, and I've done the math for a part counter. I've done it 5 different ways. I've done it once correctly, and I've done it wrong 4 times. We're going to start digging into that. So we're going to take a look at the part program that I've given you. This will be available as a Google Drive link in the video notes below. And this is going to be very, very silly motion, but the idea is that I'm going to run something in a loop to tell my axis to move, and then I'm going to say how many loops did I run through, like basically if I'm counting parts. If I was doing, for example, a operation on a turbine disk where I've got 60 blades on a disk, and I have to do the same thing 60 times in a row, I want to know if I'm on blade 39 or if I'm on blade 42 or where I am. So that's kind of the example we're going for. So I define a couple variables in the header. I define the loop counter, meaning how many times am I going to run through my loop, moving my x-axis around. I'm going to define the part counter, meaning how many parts did I make. We're going to define this as R1. Normally, I would much prefer to use a GUD here, but GUDs don't trace particularly well, so it's hard to show you. So I'm going to do it as R1. If you run this on your system, make sure R1 is actually a variable which is available for you to use, and it's not going to conflict with something, and that R1 is not storing important data for something else. I'm doing 10 millimeter steps, so just defining that as a variable. Going to clear my trace trigger, initialize my counters, do an approach move, get to somewhere safe. Then I'm going to trigger the trace. I trigger my start of my trace on trace trigger equal 1. I stop on trace trigger equal 2. This is a very clean way to do that. So we'll move at 2500 millimeter a minute, and we're going to look at loop 1. So we look at loop number 1. First thing we're going to do is we're going to set my part counter to 0. And then I'm going to run 5 loops of this. And what I'm going to do as a very silly, worthless motion is I'm going to say x equals my loop counter times my step multiplier, and then go back to 0. So I'll do a loop of go to x10, go back to 0, go to x20, go back to 0, go to x30, go back to 0, go to x40, back to 0, x50, back to 0. Just silly motion to have something moving And we'll say that after each one of these loops, I want to increment my part counter, meaning, like, again, going back to that example of doing a turbine disc, that I've finished the next slot, blade, whatever. So since I finished it, hit a StopRe right here, and I say part counter equals my loop counter. So this is going to update my R1 because R1 is part counter. I'm going to update that, throw a message. Great. Let's look at what happens in the trace. A screenshot of that. So I got my loop 1 where I go X10, X20, X30, X40, X50, back to 0 each time. I've got my R1 that I've traced. It goes from 0 to 1 to 2 to 3 to 4 to 5, exactly as it should. Because this is how this logic needs to be structured. What's also worth noting is that I don't have to have anything in the motion. Because even though I'm reading these variables here, those can all be processed in Lookahead. Because my step multiplier never changes. We define that in the header, that's 10 millimeters, it's stuck. The loop counter, every time it runs through this, even if it's unwrapping this whole loop in Lookahead, that's going to be unwrapped in pre-processing as 1, 2, 3, 4, 5. So even if I didn't have the StopRe here, that would work perfectly. What the StopRe is for is so we can update part counter correctly. Now we're going to look at loop 2. Loop 2 is screwed up and it's not going to work right. Because what it did is I took exactly the same as loop 1 and copied and pasted it, and I took the StopRe out. Same exact thing. So let's look at it. Trace, what ends up happening is I get the same motion. And the cool thing is with this example, no matter what I do to screw these things up, I always get the same motion. And also that message that I'm throwing, that message will always be correct because that message is generated in pre-processing, but it's also planned of that's what we're going to throw later. So that's already kind of just stored. So we don't need the StopRes for that. The message will always be correct. But what you'll see is that my part counter variable, my R1, it's just stuck at 5. Why is it stuck at 5? Let's look at code. Code says part counter equals 0. Okay. Then it says part counter equals loop counter like I had before. What's going on? The thing is, because this is such a short loop, this whole blob is processed in one interpolator tick before anything actually starts moving. The part counter never goes to 0 because it didn't have time to go to 0. It was just processed in Lookahead, and we blew on past it. We blew on past the loop counter. We blew past this because it was all just done in one interpolator tick. I probably had this machine set up to do 250 blocks of Lookahead. This all just got done instantly. So now we're going to look at loop 3, which I've screwed up in a different way. The way I've managed to screw up loop 3 is, again, we get the same motion out of X, which is wonderful, but our R parameter is basically pegged to 0. Let's see what I did this time. So loop 3 is loop 2 copied verbatim. The only difference between them is that I threw a StopRe between them. Okay, so shouldn't they do the same thing? Kind of, sort of, not really. What happens is that loop 2 got stuck at 5 because it finished doing the calculation Lookahead before all the machine motion started. So the end result was, in pre-processing, the result of the loop was 5. Great. In loop 3, we go ahead and normally have the part counter R1 incremented to 5 right here, just like in loop 2. The difference being loop 4's influence. I reset my part counter to 0 for my StopRe for loop 4. So what ends up happening is that the whole blob of loop 3 is done in pre-processing. Okay, R1 went 1, 2, 3, 4, 5 in pre-processing. We never actually saw it. And then it got reset to 0. And then Lookahead got suspended here. That's how we get our part counter stuck at 0 for loop 3. Loops 4 and 5, again, are copies of loop 2, but I've done something a little bit different just to demonstrate a concept. So what we see is that loop 4, we're basically stuck at a value of 5 for our counter. We're going to drop to 0 briefly, and then we're going to be stuck at 5 again. So we're going to look at these as a pair. So loop 4, we reset to 0 and hit a StopRe before we entered it. Because it's a copy of our good friend loop 2 that we know pegs our part counter to 5, Part counter gets tied to 5 immediately in Lookahead. Okay, fine. We hit a StopRe at the end of that. So this is keeping loop 4 tied at 5. So that's like loop 2 was. We hit a StopRe, hit part counter equals 0, and then another StopRe. And then we've got loop 5, which again is loop 2 without the internal StopRes that we need to make this work correctly. So what this is doing is that this is forcing me to drop part counter to 0 for a brief instant before Lookahead takes it and runs it right back to 5. The main takeaway from this video is that StopRe is necessary. If you use it correctly, it's not going to hurt your cycle time too badly. It is going to slow you down a little bit, but it is necessary for certain operations. It is required if you need to do things that are sensitive to having fresh data. So I've shown you the structure in these silly little loops. Now, one of the things that will happen is when you go to try to start debugging real world problems where you have StopRes that are missing, is that it's not going to be quite as obvious as my silly little square wave examples. Because in my silly little examples here, I've got, 5 blocks in my loop, and I'm running through 5 times, so that's 25 blocks. How many of your program headers are longer than 25 blocks? This is just so short that it's trivial, but it makes for really, really good, clean examples without all the overhead of reality. So if we look at the PDF that came with all your other downloads with your part programs and the trace, one of the questions you should be asking yourself is, hey, if there's some of these data things like probe results that we know are going to require a StopRe, shouldn't we have that built in? And the short answer is kind of, sort of. The deal is that starting in Powerline 7.4, some of the variables, anything with the prefix of $A, $V, or $R, those include what's called an implicit StopRe, meaning that they've got a StopRe built in. You're going to get the same effect as a StopRe, but you don't have to put your own in. If you put your own in, then you're doing it twice. The challenge being that Powerline 7.4, that was give or take, we'll say 2006-ish that was released. Prior to that, it was less than consistent and it was not documented.